We've already opened up SSMS. Let's connect to the TDF Lab 02 that we had already set up in our earlier episode. Cool. Let me bring up the template. Perfect. I don't need the other session. Great. Cool. Let's get started by creating a new database and then connecting to a database. All right. Let's mention create database test db, and we use the test db. Perfect. Let's hide this one. Now database is obviously created here, test db. Rather I'll just unpin it. That's better. This looks great. Let's go ahead and create a table as well. Please understand that the SQL file that we have over here, why do we mention the notes? Because that helps us recollect about what are we learning along the way. So I have pre-written all the notes that will be helpful as and when we discuss or delve deeper into certain topics. Like for the first note that we have over here is the purpose for data types is to allocate space in memory, as we have already touched upon it, and to validate the type of data that we have saved, right? And when we say type, this is something that we were referring to as nature of the data. Let's create the table. Create table. Let's create this as test table 1, and all our columns follow it over here. Call 1 as begin, call 2 as int, call 3 is. So let's just create with all the 4 types of integer columns that we can remember over here. Sorry, it's tiny int. Alright, so we have created the table. Now all these 4 columns will store integer data type. The difference is what kind of space are we allocating for each column on the memory. Okay, so the begin requires 8 bytes of storage per saved value. 8 bytes of storage per saved value. Alright. Int requires 4 bytes, 2 bytes for small int, and tiny int is 1 byte. And since we all know that 1 byte translates to 8 bits on the computer memory, so it is 1 byte or 8 bits. Sorry, that's the wrong kind of byte. 8 bits. Cool. Now let's understand very briefly, right? What is this 8 bits, and how does it help store a tiny int value? Let's quickly cover that. So back to our presentation, where we discuss a very basic concept of how is the computer memory actually storing the values using bits. Now tiny int, we already learned that tiny int has a range from 0 to 255. Okay, now how is this range determined, and how does 8-bit data translate into storage of 0 to 255 in decimal? Now when I say bits, your numbers are stored in zeros and ones, right? So that's why we use bits. So 1 bit will be used to store either a 0 or a 1. Now we just used a converter that we can find online. There's a lot of converters that you can play around with. So when we say binary to decimal converter, right, and we mention 8 times 1 and we convert it to a decimal, we see that the maximum decimal number that can be stored here is 255. Now why did I use the word maximum? Because in a full length of 8 bits, the maximum value can only be generated when we have ones for all the bits. When I say all, it's all the 8 bits that you can see over here. Now, how does it convert, right? In a very simple fashion, you raise 2 to the power 8, okay, the number of bits that we have, and you do a minus 1, then you'll arrive at 256 minus 1, that is your 255. Let's not go into details of covering how to convert a bit to a decimal, that is a base 2 number, binary number, to a base 10 decimal number. It's out of the scope of this particular session or the episode. Rather, why don't you do some searching and then let me know if you have any questions. As you have seen that there are no sign associated with a tiny int number, hence we do not need the sign bit, unlike what we have for float or real and int, small int. We don't have a sign bit for tiny int. So sign bit is essentially there's a particular bit that is stored just to store the sign of the number, whether it's a negative or a positive number. Now, as we have touched upon how to convert your binary to decimal, so this is the long form of conversion, wherein you start from the units place, units, tenth, hundredth, thousandth, and you multiply it by 2 to the power 0, 1, 2, 3, continued to up until 7, and you get this number. And the short, the quicker version of converting it is 2 to the power 8 minus 1. Now let's get back to our SSMS and discuss the remaining practicals. Perfect. Now let us insert few values, right? Otherwise, what's the fun in creating a table or the purpose? Cool. Insert into test table 1 values. Let's specify here 1 5 times 0, 1 comma 20k, 1200 and 255. And let's show you another example where we breach the limit, say for the tiny int, right? So this is perfectly fine, inserts itself into our test table 1, but this one should not allow us because there's an arithmetic overflow error for data type tiny int, since we have already discussed that tiny int allows us to store numbers up until 255 because that is the maximum space that is allocated. Okay, cool. So values should be within our acceptable range, and this particular one throws an error. Cool. Next up, let's cover float data type. For that, let's create another table. We will reuse the block of code that we already have, name it as test table 2, call 1 as bit, then decimal 3, 2, and let's have real and float. All right. Perfect. We should remove these because these are no more applicable. We'll certainly mention how many bytes they take. Perfect. Let's first create this table and let's start with discussing decimal. We will cover a bit in a moment. That's very easy. So whenever we declare a decimal, you'll see in the brackets we have two parameters, right? So the first one is your precision, or it denotes the maximum count of digits that can be stored in the column. And the next one is your scale, or the count of digits to the right of decimal point. Okay, there are a few rules around this. That is, your scale should be less than equal to your precision. That is not a rule, but that is a common sense of fact, because when you're defining the total number of digits as 10 inclusive of the numbers that you have towards the right and towards the left, obviously towards the right cannot exceed your total length, right? So that's there, and that the total number of digits will not exceed 38. Let's summarize our notes over here, and do remember that the decimal takes a space of about 5 to 17 bytes. Perfect. Let's discuss. Let's come to know what do we mean by real and float. So real has a precision of 7 digits. Again, when I say precision, it means the total count of digits. The storage space that it takes is 4 bytes, and the ISO synonym for real is float 24. And when we talk about float, the precision is 15 digits and the storage is 8 bytes. Now we'll come to the fact of why did we refer to real as a synonym for float within brackets 24. Let's mention our notes over here. Here, precision is 7 digits, storage of 4 bytes, and the ISO synonym for real is float 24. Cool. And for this, the precision will be 15 digits, and the storage space of 8 bytes. Cool. Perfect. Let's now understand in depth what do we use the float for, and why do we mention a number within the brackets over here. So n, that is the number stored as 50, not stored rather, it's specified as 50 for declaring call 4, is the number of bits that will be allocated to store the mantissa or significant of the float number once it is converted into a scientific notation. Now, next, let's touch what do we mean by scientific notation. Say for example, we have a number that is 650 million. In scientific notation, it can be written as 6.5 multiplied by 10 raised to 8. In this example, 6.5 is the significand or your mantissa. The 8 is the exponent with a base of 10. Okay. Now, in float, right, whenever we have the n between 25 and 53, it will be treated as 53. We'll come as to why it is doing that. Now remember, we already mentioned, right, that the float will use 8 bytes, and 8 into 8 we have 64 bits, right? So 64 bits will be used to store your mantissa or significant plus exponent. Okay, but do remember, we also can store the sign of that number, whether it's a positive number or it's a negative number. So how do we store it, right? So now we have 64 bits. That's very clear for a float. Now within this 64 bits, right, one will be used for storing the sign bit, whether it's a positive or a negative. 52 bits will be used to store your significand, and 11 for your exponent. Now when you add up all these 3 bits, you will see we arrive at 64 bits or a total of 8 bytes. Now do remember that there are chances for your significand or mantissa to be rounded off. The very reason for this is, say we have a number or a fraction. For example, let's take a pi, right? 22 by 7. So in such ratios of fractional numbers, there's a string of never-ending digits post your point, right? So it will be 3.141592 dot 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 dot. Okay, but whenever those kind of numbers or similar nature of numbers are stored in a float, obviously the storage that we allocate for the mantissa won't be enough to include all the never-ending scale, okay, after your decimal. Hence it will truncate and round it off. That's where float gives you the flexibility of storing a higher precision of a decimal, okay, compared to real. Hence, when you see the n within float mentioned any number between 1 to 24, it will be treated at 24. And when we say float 24, it can as well be treated as a real number, okay, because real has a precision 7 digits and the storage is 4 bytes, that is 32 bits, that is half of your 64 bits. Hence for real type, it is often referred to as being the ISO synonym for float within brackets 24. Hope that made it pretty clear. Let's move on to our next topic. For this one, let's introduce you to a keyword, declare. Okay, so we declare a variable, declare data type underscore binary for a binary number, okay, and we print the data type over here. Why type it again? Let's reuse this. Now when we declare data type underscore binary, so data type underscore binary is nothing but it is a placeholder that is pointing to a memory location where 12 is being stored, but 12 is being stored as binary, okay, and the format of the storage, or rather the boundaries of storage, is binary within brackets 2. Now coming to what is binary, definitely we would like to know that. Now binary is a sparsely used and for storing raw binary data to up to 8000 bytes. The number inside the parenthesis that we see, it defines the size in bytes, and remember, it's not the character length. Hence in the output what we see is a hexadecimal notation for 12. So C is essentially 12, okay, in a hexadecimal. and the part that you see here as 0x, it isn't a part of the value, it is an indication that the value that has been stored is binary and not a string. Hope that's clear. Let's move on to bit. We'll use declare notation as we move ahead. Let's declare this data type as bit and we print it, but we need to declare it as bit, right? Cool. So when we store 12 into a bit type variable, what we get in return is 1. Essentially, if I use say -12, I'll also get as 1, and if I use 0 over here, I'll get a 0. Okay, so any non-zero number gives or returns a 1. Return is a wrong connotation over here, but any non-zero number is stored as 1. Only 0 is stored as 0. So bit can be practically used to store true and false for any reporting solutions that we are developing. I mean, it's the most efficient usage of space. All right. Next up, let's cover char. Okay. We will use variable declaration for this. Declare data type char. Let's give it 30 bytes equals the data factory. Cool. Let's print it as well. Okay. We will repeat this to understand nchar, varchar. Perfect. Let's understand the difference between char and varchar, also and varchar. Now, each character needs 1 byte storage space when we declare it using char, and for nchar, each character will use 2 bytes. The difference stems from the fact that nchar allows us to store a character in its Unicode standard of character encoding, thereby enabling us to cover widest array of written languages possible. Now, here what we have used is these set of characters, the data factory, and the total count is 14. But when we store it in char or we store it in nchar, the total allocated space is 30 for char, and for nchar the total allocated space is double that of char because it allows us to store the Unicode standard. Okay. In case of varchar and nvarchar, it will only use space that is less than equal to 30 bytes. So in this case, varchar will use 14 and nvarchar will use 28. Let's run them. Let's move to our next data type, that is geography. Please note, what follows is recommended for SQL Server programmers and is optional for BI or data analysts. Geography is a spatial data type that is implemented as a .NET Common Language runtime in the SQL Server. Now, if a question arises, what is a CLR? Just remember, it is a programming that manages the execution of programs written in any of several supported languages, allowing them to share common object-oriented classes written in any of the languages. Okay, let's move ahead and create a table. Cool. Create table, spatial table demo, id int, geocol1, geography, and let's insert geography data into this table. Insert into spatial table demo, values, id as 1001, and the geography data we have already mentioned over here should be fine. Let's copy this and create another record. With geographical representation of a polygon instance. Perfect. Finally, let us select data from this table. Let's run this block of statements. Perfect. So what just happened, right? Let's move to the place where we created the table. Okay. So the second column, you see it's a geography column, but the third column over here, it renders the geography column into its Open Spatial Consortium or well-known text representation, and it uses the st as text method. You can consider this as string as text method. Now, whenever we are inserting values, we are inserting it for two columns. Okay, one is for the id and the second one is for geocol1. The third column, geocol2, is automatically storing the well-known text form of the data. Okay, and after inserting this data, when we do a select star, we can see that the first column is storing the geospatial data in its binary form. Okay, perfect. Let's move on to the next data type, that is row version. Let's create a new table. Call1 as timestamp, call2 as row version. Okay, whenever we run this query, we get an error mentioning that we can only have one timestamp column. Do note that timestamp is the synonym for row version data type, and Microsoft recommends us that we use row version for all DDL statements. The timestamp syntax is deprecated, and this feature will be removed in a future version of Microsoft SQL Server. So that is an important point for us to note. Row version is generally used as a mechanism for version stamping table rows, and the storage size is 8 bytes. What is version stamping? Version stamping is nothing but a counter that sits for every row that we have in this particular table. Whenever we make inserts into the table, the value of this particular column that represents our row version is assigned with a value that is relative to the rows already present, but note, please do not compare it with clock time. Additionally, say whenever we update values for few rows, okay, let's pick a particular row within this table. On every update, the particular row version data also increments itself. Now, we might think that this is a very good candidate for an ID column, but that's not the case. Because whenever we update values for any row, since the row version data updates itself, since it's a counter, right? Hence, the ID is always changing. Hope you get the point. Perfect, let's move ahead. We'll create a table. Let's create this table itself, right? Wherein we can have call 1 as ID and call 2 as row version. Why am I mentioning ID over here? It should be int. Perfect. We will insert into this table. But we only insert call 1, okay? Let's say 1 and make 3 inserts. Cool. Execute this set of statements. Okay. Okay, we missed out on creating the table in the first place. Let's create it. Perfect. We will check the records. Select star from row version table. As you might see over here, we have 3 records and their row version counters. Okay. Let's move ahead and cover the last data type for today's episode. That will be SQL Variant. Now, SQL Variant is to be used only when we are unsure about the type of data that we are storing in a column or for a column. Okay, and when we say that we are unsure, it's about the nature and size. Okay, it can be any of these or both as well. Let us create a new table. Create table SQL Variant table and have just one column for demonstration purposes for SQL Variant. So we have the table and let's insert all kinds of data to demonstrate that it will accept whatever is given. There are some exceptions, but you can read it up on the SQL Server documentation that Microsoft has. But mostly it accepts all the type of data that we will insert. Okay, let's have 1001 integer ABC 5.99 decimal. Also, let's have a date too. Okay, cool. So all the inserts were successfully made. Let's select the data and verify. Perfect. Great. Thanks for watching this episode. Hope this was helpful. Stay tuned. Cheers. Bye.